So, suppose we have a function f of two variables, x and y. Then we can have the gradient of f as a function of x with y held constant. For example, suppose that x is along the east-west direction, pointing east, and y is along the north-south direction, pointing north. Then, if we were to walk along the easterly direction, walk towards the east, then we would see the gradient of our hill. Perhaps it slopes upwards in the easterly direction, and we would be walking up the hill. So that would be the gradient of the hill as a function of where we are along the east-west axis towards the east, without changing our position on the north-south axis. And we can write this gradient using the following notations here. This is the most complete notation. And we would say, for this notation, the partial derivative of f with respect to x with y held constant. Now, because this function is only a function of two variables, x and y, if we're taking the derivative with respect to x, the partial derivative, then rather obviously y is what is being held constant, and so we can drop this additional notation here perhaps and just write this simpler form here. So we pronounce this kind of notation partial df by dx, and to be explicit we might add with y held constant. And this funny little symbol here is a kind of a d, and we might call that partial d. Similarly, if we were walking on the north-south direction towards the north, perhaps along a positive y direction, without changing our position along the east-west direction, so with a constant x, we would experience the gradient of the hill in that north-south direction when walking north, and we could write that as partial df by dy at constant x. Or again, if it's obvious that x is being held constant, we might just write this simpler notation. And now we have partial df by dy. So let's look at some partial derivatives by looking at slopes on this function that we've got over here. So this is our function f of x and y. So here's the x-axis, and along there is the y-axis. And we're saying, therefore, we've got some surface, this is our hill perhaps, with a height f of x and y. It varies obviously with the coordinates x and y. So at some specific position here, the value of the function, the height here, is f of x naught and y naught at the position x naught, y naught. So let's rotate round and look at the slopes along specific directions. And now we're going to be looking at the slope along the y direction with x held constant. So everywhere along this black line here is a specific constant value of x. And what we're going to be looking at as we change y along here, we're going to be looking at this slope here. So along the y direction, at this point, x naught, y naught, the rate of change of height with y at constant x is given by the slope of this line here, this orange line. Rotating around to look at the other side now, we're going to be looking at a point x naught and the gradient round about there as we change x along a line of constant y. So this black line here is a line of constant y. So y equals y naught. So again, along the x direction, at some point x naught, y naught, this point here, the rate of change of the height with x at constant y, so that's along this line here of constant y, is the slope of this orange line now. So we can also form second and higher order partial derivatives. For example, here partial d2f by dx squared or in this more complete notation here, explicitly saying we're holding y constant, is a second derivative, a second partial derivative. And just as for the ordinary second derivative, it's a measure of the curvature of the function. In this case, explicitly, the curvature of the function f in the x direction. So let's look at a specific function here now that we see in both the x and y directions. And this particular one is a function that is kind of a dome here. So high in this point in the middle and smaller at the parts around the outside. And also we could be talking about the second partial derivative d2f by dy squared. Again, we could write that more explicitly with the x held constant here. And this is a measure of the curvature of the function in the y direction. So for this particular function, for example, if we move along this line here, we see that as we increase x up in this region, the gradient is going from positive over towards negative in this part of the function. Therefore, d2f by dx squared in this region here is negative. And similarly, if we're looking at d2f by dy squared, anywhere at the top of this dome, d2f by dy squared is similarly negative because we're changing from a positive gradient towards a negative gradient. We could also look at a function that was the other way up, that was a minimum down in here. And similarly, as we move down into that minimum, now we're seeing that as we go, say, along the x direction, a negative gradient heading down into the minimum is turning into a positive one as we come back out the other side. So d2f by dx squared here, the partial derivative, is positive. And similarly, in the y direction, as we move along y, we're going from a negative gradient in y to a positive gradient in y. So again, partial d2f by dy squared is greater than 0. And it's also possible to have functions where one of the second partial derivatives is positive and the other one is negative. So here, as we are going along the x direction, for example, suppose we're in this region here, we're going from a negative gradient along x, we're going downhill for positive x, to going uphill for positive x. So that's a positive second partial derivative, d2f by dx squared. But in the y direction, as we go along one of these lines in this middle region here, we have a negative second partial derivative, d2f by dy squared, because we're going from a positive gradient in y towards a negative gradient in y. And this particular kind of curve is sometimes called a saddle point, for rather obvious reasons, because it looks a bit like the saddle that you put on a horse. Now, with partial derivatives, we can get something that we don't see with ordinary derivatives, which is the cross derivative. This cross derivative here, you see, has got second order d2 on the top line, but it's got dx and dy on the bottom. So this is partial d2f by dx dy. And what does that mean? Well, we can have a gradient df by dy at constant x. And what we're asking is, how fast does that gradient change as we move along x? And this particular kind of entity here is a measure of how warped a surface is. So here's a somewhat warped surface. And what we can see here is that if we look at df by dy, it is negative here, so we get a negative gradient, and as we move along x, that turns into a positive gradient. So the gradient df by dy is changing from being negative to being positive as we move along x. That means d2f by dx dy, the partial cross derivative, is greater than 0 because we changed from a negative df by dy to a positive df by dy. Note incidentally that for ordinary smooth functions, it doesn't matter which order you do this in. And I'm not going to prove that to you, but if you think about what's going on with calculating these various cross derivatives based on the values of the functions at points, you can actually prove that these are the same thing. We can also look at a function that's warped the other way round, and in this case, partial d2f by dx dy is less than 0. So we had a gradient here in the y direction that was positive, and as we moved out to larger x, it became negative, and that would give us a negative cross derivative.